Okay, so greetings to everyone. Okay, we will speak briefly on how we are moving our first steps, okay, in quantum computing and in business application of quantum techniques. Okay, I will speak, introduce this quantum clustering, our exploration of quantum clustering. Then Giulio will describe you our first results that we achieved with Quera and using their technology. Just for, let me briefly introduce who we are. We are, a global consulting firm. We are, I would say, globally widespread. And in particular, we have a very strong technological fingerprint. Okay, we have about 600 professionals dedicated to data science and cloud infrastructure, technology, and every other applications. Okay, our past experience in data science is the beginning of thinking about how we can apply quantum technology to business-related problems. And yeah, speaking about this, the question is how many ways of applying clustering are there? Yeah, thinking about this very, very wide table of applications that our experience, about 10 years of data science, tells us, yeah, you can say, yeah, thinking about clustering is interesting and maybe is a business problem that someone wants to tackle in any case. Okay, so we went on thinking about this stuff, but how did we focus on clustering? This is the question. And here the idea is that we didn't start from a general clustering problem. We began with a geographically related clustering problem that doesn't start from a clustering by itself, but starts from a more general question that is a NP-hard problem. This is quite known. The traveling salesperson problem. So how can we optimize maybe the route of a person moving towards points, or the route of a squad that have to solve some tasks? We know that this is a complex, computationally complex problem, okay? And actually, this is stuff that data science is able to tackle classically with greedy algorithms and suboptimal solutions, okay? So the question is, okay, can we tackle this problem in some way? And where we can use quantum? Okay, here the idea is that that problem, usually speaking, with a general business-related problem, something like thousands of points is too big for being treated easily in any case. So the idea is that, okay, we can use a divide and conquer approach, and that is how clustering emerges as an application here. Simply, how can we divide the huge graph before in some compact structures, some geometrically speaking compact subsets, and then solve the problem of the TSP inside the simple, the smaller stuff. Okay, this is a problem that can be translated into many business applications, okay? Utilities, automotive, logistics, whatever. It's to your idea of thinking what kind of problem you had that is can be reconducted to this stuff, okay? And yeah, so the first step of this is find the clusters, and we went on trying to solve the problem of clustering on a quantum environment. Okay, I will leave to Giulio to explain you how we went on in thinking whether clustering could be a problem that can be easily or not so easily solved on Quera. Thank you, Quera, for giving us this opportunity.
Yes, and indeed I want to thank Quera myself. We are using Aquila, their latest analogical device. And yeah, so what is the solution pipeline and kind of the project that we've been trying to develop? So when we look at this kind of problem, we see like 5 main steps. So there is a step of data preparation, then there is manipulation of this data ingestion, then there is algorithms, then there is the computation actually that is being performed, and finally there is some KPI calculation. So these 5 steps that I've been showing you here are steps that are typically and common also in a classical approach. And many of them are easy, and I just want to stress that, okay, you have your data points that are geographically displaced, you prepare them, you clean them, and then you can do some classical algorithms again. You can use k-means, dbScan, and so the typical idea about these methods is, okay, you try to geographically group these points, and there is typically a tuning phase, because sometimes there are hyperparameters in these algorithms that need to be tuned. For example, here, these points have been divided here in just 3 clusters. However, it's not the best selection, because you can see that these points are grouped in 4 clusters. And so you need to do this parameter tuning in order to indeed find the best solution. And once you do this, of course, you need to do this for all the algorithms that you have. Then you can compute some KPIs and some figures, some quantitative figures to highlight how well you did and how well you did not do the clustering problem. And so what we try to do is, okay, let's substitute the algorithm itself and try to develop something leveraging Quera. And then, again, find again what are these KPI in this scenario. Here, of course, we needed to scratch our heads and learn something, because although, let's say, the preparation and the ingestion of data points and the algorithm is very easy in the classical setting, this is not so easy in the quantum one. And indeed, when you look at the classical scenario, an algorithm is just 3 lines of code in Python. Maybe you have 2 or 3 parameters that you have to tune, and everything is very easy. But however, here in Quera, we know that we are playing with Rydberg atoms. It's much more complicated. You have a full Hamiltonian with time-dependent parameters. And also, we were not even sure what was the look of the solution, and if this kind of algorithm could even work. And even more so, you have to be careful, because you have many more parameters to tune. So for example, in the k-means algorithm, you just have the number of clusters that you want to divide your points in. Or in the dbScan algorithm, maybe you need to select the distance, the minimum distance of points in order to consider them belonging to the same cluster. Here instead, again, we have many parameters. So we have all the tuning, the distance between the atoms, and even more so, you have technical limitations, because right now Quera just has a certain platform with some maximum distance of the system. There is a minimum distance between atoms. There is an interaction Hamiltonian that goes with the distance between atoms. But so there were many questions to be asked. And in order to generalize this problem, we actually thought, using and leveraging our data science background and machine learning background, we tried to, again, generalize it and trying to think about not only points that are geographically displayed randomly, but maybe also other kind of data sets. So for example, a circle data set. So in this case, points are organized in circles, in concentric circles. And this kind of data set is really interesting from a machine learning perspective, because, for example, a legacy algorithm like k-means is not able to distinguish the complex structure of this data set. So if you try to divide with k-means these points, you will just try to split them into spheres of equal dimension, of equal radius. And this, of course, fails in capturing interesting complex features. And then you can do many more things. And indeed, that's what we do. That's what we did. We consider even more data sets. A blob data set is the one with points that are well distributed already. And this was in order to understand if a Quera-based algorithm would work very well. And then we also played with other complex data set, with Moon data set, with King's data set. That is something that Quera guys are really doing a lot. And we just tried to see what was going on. So what happened? And why and how does clustering with Quera works? So I don't want to go too much into the details, but just to give you an insight of what's happening. So classical algorithms, and I'm sorry for this misdisplayed, but okay, something went wrong with the conversion of the file. Anyway, classical algorithms, being k-means or dbScan, they rely on the positions of points, just on the positions of points. And due to that, you just have information regarding n points that are the n points of your data set. However, the Quera-based algorithm works in a different way because leverage the analog dynamics associated to the Hamiltonian, the time-dependent Hamiltonian that you choose to model your problem with. And so the idea is that you try to set your points as locations of atoms, then you let the dynamical system evolve, some correlations will be developed, and then you use this kind of information, so both the information on the points location and the correlation matrix to perform a clustering. This then gives you much more information because you have, again, information of n points and then an n squared matrix. So due to that, okay, just an idea. So clustering in this way, it's thought as an optimization problem where you try to minimize the edges connecting points belonging to different clusters. So this is just an idea. It's related to the max cut problem, actually the min cut problem for the technical ones here. And due to the richness, again, explained here, and I'm really sorry again for this problem, due to the richness of the data that we analyze with the quantum-based algorithm, we might expect an ability to understand complex data structures. However, we have also some issues that you have many more parameters to be tuned, and you have to interpret the results correctly. And this is something that was really a point, really trying to understand what were the parameters to tune, because again, you rely on your algorithm not only on the location of points, but also on the correlation matrix. So going through the results, just some qualitative results right now. So here on the top, we will see some points. These are belonging to the blob dataset, so well-distributed points geographically. We will see 3 panels on the left-hand side. Yes, left-hand side, sorry. We will see k-means. In the middle, we see dbScan, so the 2 left panels will be classical algorithms, and on the right-hand side is a Quera-based algorithm. So here, as you can see, in particular, looking at the difference between the Quera and k-means, which is the legacy classical algorithm, we see that Quera actually was able to perform quite well qualitatively, because you see that we have 3 clusters on the left-hand side and 3 clusters on the right-hand side. Another example here, we see again 3 clusters from k-means and 3 clusters again from Quera. Okay, there was a point that was considered belonging to the red cluster from Quera, but I mean, qualitatively, it's something that was interesting. And this is more of the same when you play with other kind of data set. It's similar stuff. And here again, we have other kind of data set on the bottom. I don't know if you can all see that, but these are geographically displaced algorithms. And again, the geographically displaced points. And we see again qualitative agreement. Maybe not all points are in agreement with k-means, but we have a good agreement. And with these examples, we could say that a Quera-based algorithm works, which is something that we wanted it to be. But of course, you just do not need something qualitative. We wanted a quantitative result. And in order to do so, we computed a KPI, which is the silhouette score, for many different data sets belonging to all the different types of data set that I introduced before. And so this is the statistical results that we obtained. So on the red, we will have all k-means, and on the blue, we will have Quera. So the classical with respect to the quantum algorithm. And we see here plotted the count of times that the algorithm generated a silhouette score belonging to one of these bins. And the silhouette score in particular is a quality score associated to the quality of clusters, and is very good when you go on the right-hand side, close to 1, and not so good when you are on the left. But here we see that in all of these, when you look overall, you see an agreement between these 2 kind of approaches. And even more so, if you look at the different types of data set, we will see again an agreement. And the most interesting ones for us were the ones related to a blob dataset where the points are well distributed, and we see that the Quera algorithm performs really well. And also when the points are geographically displaced in 2D. And we indeed see, again, a very nice agreement. If you really want to see all the difference, you see how you can compose the red histogram that I showed you before, and the blue histogram. Again, we see an agreement. And in particular, we see even something better being done with Quera, looking at specific data sets. So for example, for the blob data set, we really see some nice features. And so this is one thing. The last thing before leaving you with our conclusion is something that we noticed that cannot be captured with the silhouette score KPI. And this is the fact that sometimes, as I told you, with Quera, we are able to capture complex data structure that were not able to be captured with k-means. And by this, I ask you to look at the bottom plot here. Because here there is a data set. It's one example. We witnessed this behavior in other data sets, of course, where points are organized in, again, two circles. And the classical algorithm divides these points. The best optimal way for k-means to divide these points is to divide them in 4 or 5 clusters, depending on the data set, but is not able to capture this complex structure. And instead here, with Quera, we are able to see 2 concentric circles. So a cluster that is composed by the points around, and then another cluster being composed by the points inside. And so this was really interesting for us, and we think it's really interesting. We want to push this even further. Also because, as I was telling you, we believe we will be able to understand even more when we will do some more work about this, but it's really promising. And so with this, I leave you to the conclusion. We learned a lot about the methodology and about Quera. I think it's really interesting. I think it's really nice machine. We found comparable results with k-means, and now we are really eager to look for more complex and larger data sets in order to appreciate the capability of Quera in understanding this kind of features. So with this, thank you very much for your attention.
Thank you, Giulio. Any questions from the floor?
Hi, thank you. So my first question is, the heuristics that you compared to are relatively cheap to perform. Do you have any reason to expect that your Q-era algorithm scales favorably compared to the heuristics, the classical heuristics?
So we expect to work. So the most interesting thing for me when I think about this is that I see a good agreement with classical algorithms, but also I see some flexibility. So I see ability to compare well with k-means, but also, again, get these complex data structures. So I think this is something, to me, really interesting. So, yeah.
So another is that, do you have any way of simulating a non-fully connected graph?
Because a non-fully connected graph.
Yeah, so here you were, every point in this example had like a connection, had an edge to every other point, because they all had distances, yes. And you made it physically with the atoms, and the atoms have correlations based on their distances.
Yes.
But often graphs have nodes that have no edge between them. Do you have any way of implementing that in your algorithm?
So Quera in itself really plays well with these geometrical locations of points, and where there is a distance which allows you to consider 2 points correlated or not. So in this sense, this kind of algorithm and this kind of method really plays well with geographically located geographically located points. If you would have a fully connected graph, you would need to do an encoding, or like there is some gadgets that they develop in Quera where you have to remap your initial graph into a larger graph, but you have like a overhead in order to map these two data sets. In general, I think it would depend specifically on the problem that you have to consider. Maybe you have to analyze well your problem and do some pre-processing even before putting your graph into Quera. But I think this depends really on the specifics of your problem. So.
I'll keep going. Yeah, so last thing, your DB scan results looked awful.
Yeah.
Why?
They did.
What happened there?
What happened? So, okay. What happened is that we considered a distance that was fixed for all the different data sets. And the points were not, so the distance was selected, let's say, from a business-related reason. However, when you have points that are very close to each other, DBScan considers them all belonging to the same cluster. Because, so, okay, here everything is rescaled to be from 0 to 1. But like, let's say if I have, if the distance I selected is too large, then every point is belonging to the same cluster. And I agree, you could tune that, of course, you could improve on that. But the question is, let's say also k-means, if you have your circle data set, you could think of a pre-processing step where you say, okay, I encode my points not as x and y, but I encode them as r and theta, like an angle, and then it works well. But the point here is trying to do clustering without having information on your dataset. So I blindly try to go for my algorithm. So I don't, let's say I have my business-related reasons, I fix them, and then I blindly go. And then I see if I did well or if I didn't. Because, I mean, if I know already that there are circles, and then, okay, everybody is good in doing that. I mean, also my cat, I don't know. But yeah, so again, we did it blindly. So, but I agree. If you know what is let's say, if you know your scale, then you can tune it before doing DBScan. But if I just have a business reason in mind that I need to set that, and then I do the algorithm, DBScan in this case would perform not so well. And also DBScan, for example, would not work so well if you have clusters that have different densities. So you also have to take care of that. This is something that we want to explore as well. Because if you have clusters with different densities, DBScan does not work well because, again, you would not find the best matching distance for the two different kind of points. So again, let's say, when I think about this, I think in two directions. So either I try to look at flexibility or I try to look at performance. And right now, what I'm seeing is, okay, it seems very flexible. So this is my extraction of information that I can give you. But we will have to understand more. So.
Anything else? All right, Matteo and Giulio, thank you so much for finishing the session.
Thank you very much.